Hello again. This is Math 1120 coming to you from the College of DuPage. And the title of this lecture is General Energy Considerations, including non-conservative forces. Please be an attentive learner as you watch this video. Conservative and non-conservative forces. Earlier in this set of lectures, we discussed several problems involving work done on an object by conservative forces. In those problems, the work could be described completely in terms of changes in mechanical energy. The total mechanical energy, kinetic plus potential, was conserved. We also hinted at methods for dealing with problems involving forces that do work. And these work others can't be described in terms of potential energy, and these non-conservative forces are what we're going to talk about in this lecture. So first we're going to revisit a problem we looked at before, but now we're going to add a non-conservative force to the mix. So this was the position, the problem we looked at before, and many of the parameters are going to be the same. For example, the spring constant is going to be the same, and this is the general setup, but we're changing a few things. So let's talk about what we're changing. So suppose the glider is initially at rest at x equal to 0. Okay, so we're initially at rest at x equal to 0. And the string is unstretched. Then you apply a constant force F with magnitude of 0.610 newtons to the glider. So that's what's new. We're starting at rest and we're applying this force to the glider. So it's pulling it out this way. Now, as you learned before, as it's pulling it out this way, there's a compensating force that's happening here with the spring, and so that's got to be part of your deliberations. So we ask the question, what is the glider's speed when it is moved to the point x equal 0.100 meters? So you see you're starting at 0, you're pulling it out, so this is x initial, that is velocity initial. And you want to know how fast is it, what's its speed when you reach this point. X final equals 0.100. And so you got F pulling this way, but you also have V final. So again, we're introducing a new force. You know what to do. Let's see how you did. So let's consider the picture that we have up here then. We know that the initial kinetic energy is 0 because we're starting at rest. We know the final kinetic energy is equal to 1/2 mv sub f squared, and so that is what we have at this point over here. That's the final kinetic energy. We know the initial potential energy is 0 because the spring is not disturbed from its equilibrium point. And when it's pulled out to this dimension, we know that it is 1/2 the spring constant 1/2 k, and then it is times x squared. So x final was 0.01. Put that in and square it. We do the multiplying and we get that this is what we get for that. And the other, we know that this force of 0.610 newtons is applied through 0.1 meters, and so I multiply those things together, and that means that this is 0.0610 joules. So that is the force that is being applied times the distance, which is the work. That's the other work. Okay, so now we're going to put this together then. So we have that the final kinetic energy plus the final potential energy is equal to the initial kinetic energy plus the initial potential energy plus what was added to the system. So this one is going to be 1/2 m, and that's V final squared. Now we don't know what V final squared is, so we're going to solve for that in a little bit. But then we know that the U final was this 0.0250 joules. That was strictly from here. So those two are equal to these initial values were 0, and that's going to be the other work. That's what we have initially, is the other work. And so the only unknown we have is V sub t, or V final squared, and we solve that either using a quadratic formula. In fact, I think we have to use a quadratic formula to solve that, and so we're going to get V sub f is equal to 600 meters per second squared. So that is the answer to the problem. Let's look at another example. In this example, we're also going to be referring to a problem we've talked about before, and the problem we talked about before was the quarter pipe that we have here. Now the reason that's a quarter pipe is you can think about this as being a total pipe, and this is 1/4 of that. So this is the quarter pipe that's used for skateboarding, and you have these values of your variables. The mass of the lad, including the skateboard, I guess, is 25 kilograms. That was their initial velocity, but then they jump out. The radius of this circle is 3 meters. That means the distance from here down to here is 3. And down here the guy is moving with a velocity. Okay, so in this example, and we did this in a previous example. In this example, we calculate the change in mechanical energy in order to directly determine the work done by the non-conservative force. So now we're saying, oh, there's some friction on this. Before we took that to be a frictionless thing. Now suppose the ramp is not frictionless, and the skateboard's poured at the bottom, speed at the bottom is 7 meters per second. Now on the earlier example, he was going faster than that because we were letting this be frictionless. So the question is, what work is done by the friction force acting on him? You know what to do. Let's see how you did. Now, I talked about what the picture was before, so we have this up here. We're choosing the same initial and final points and the reference level. And in this case, the work due to friction is the work other. So the quantities are going to be this. The initial kinetic energy, when you're at the top, you're not moving, so that's going to be 0. And the initial potential energy is going to be, it is mg, the weight of the skater and his skateboard, and the height is going to be the radius of the circle, which is going to be r, which is 3 meters. So we plug in all of those numbers, and we have that the initial potential energy was 735 joules. Now the final kinetic energy is 1/2 mv sub final squared. So there's 1/2. This is 25 kilograms, and we said that we measured it, his final speed in this problem was 7 meters per second. So this is 1/2 mv squared. You do all those calculations and you get 613 joules. So we have to solve this equation because W other is the difference between those two. So this is the final kinetic energy minus the plus the final potential energy minus the initial. This is the only other factor in town. So this one was 613. Those two were 0 minus 735 joules. Now when you take the difference between these two, you get minus 122 joules. That makes sense because it's opposite the direction of the motion, is the force done by the frictional force. And the total mechanical energy decreases by 122 joules. And we were supposed to find the work done by the frictional force, and that was this negative 122 joules, or we could have said the amount was that we decreased by 122 joules. Let's look at a more complex example. Here we're loading a truck. So this guy's down here, he shoves it up, and he shoves it with enough energy that he expects it will reach the top. But he underestimated that there was friction here, and so he only got part way, so then it slides back down like that. So that's the general story. Let's read the details. And the title of this example is called Loading a Crate onto a truck. In our final example in this lecture, we will add friction to the inclined plane. So there's friction on the ramp this time. Of course, friction does work, and we will need to determine its contribution to the work, and this is the work other. So a crate full of machine parts sits on the floor. The total mass is 8 kilograms. The crate must be raised to the floor of the truck by sliding it up a ramp that is 2.5 meters long. This whole thing is 2.5 meters long, and it's inclined at 30 degrees. So this angle is 30 degrees. So this is the inclined plane problems that we know and have worked before. The shop foreman, this guy, giving no thought to the force of friction, calculates he can get the crate up the ramp by giving an initial speed of 5 meters per second at the bottom and letting go. Unfortunately, friction is not negligible, and the crate slides up 1.6 meters only, falling 0.9 meters short, as it turns out, and then starts sliding back down. And then it does get at the bottom, and G, the question is it still moving when it hits the bottom? And you've got gravity working on it, but friction is retarding the motion. So we're saying, what is the velocity down here? So just to continue reading, so it slid up 1.6 up the ramp, stops, and then slides back down. So that, and the picture shows the situation here. Assuming that the friction force acting on the crate is constant, that's a good assumption, then we're going to find the magnitude. That's the magnitude of the frictional force. That's part A. And part B is, how fast is the crate moving when it reaches the bottom of the ramp? That is, what is the magnitude of the velocity when it gets down there? You know what to do. Let's see how you did. Okay, we have 3 points that we'll have to reference here. The ground point, which is called point 1, and by the way, later on we're calling that same point point 3. But this point 1 and point 3 is the point where the crate stops on the, that's the where it starts, and where it, we want to measure its velocity is point 3. Point 2 is where it stops going up from the shove the guy initially gave it. So that is point 2. We identify points 1 and 3 separately because the crate's velocity is different going on the return. So for part A, point 1 is the initial point, and point 2 is the final point. So for the first part, we're just going to say, hey, he started it, he shoved it up, and then it stops. Where are those points, and what's going on at those points? For part B, point 1 will be the initial point, and point 3 is the final point. Okay, so for this part A, and remember then in part A, we're just really trying to find the force of friction. Okay, so here's part A, here's the equations we set up. Now the first thing that we want to do is, how did the potential energy change? Well, the potential energy changes by this amount right here. Again, the potential energy here is gravitational potential energy. So going from here up to that point, how far did it go? Well, this was the hypotenuse, which is 1.6. The angle is 30 degrees, so that is going to be the 1.6 times the sine of 30 degrees, and so that is going to be 0.8 meters is that distance up and down. So you see that is the potential energy at the final point, or at least that's the distance. Now to calculate that, what we're going to do is we're going to take the mass times that height times the acceleration due to gravity, and we get that the kinetic energy up there is 62.7. So, and the kinetic energy that we started out with was 1/2 m, and this is v squared, and he started this out at 5 meters per second, but that is 1/2 mv squared. And so what happens here is that calculation is going to give you 100 joules. Okay, so and then the force other, or work other rather, is going to be minus the force of friction. We're trying to move against the force of friction times s. So this is going to be minus f times, and this acts through a distance of 1.6 because it acts all the way along the ramp. So let's look at the overall equation then. So the when we start adding the initial kinetic energy and the initial potential energy and the work other over here, that's going to be equal to the final kinetic energy, or the kinetic energy at point 2. I guess we were calling these point 1. So this is at point 2, the kinetic energy, it stops, and the potential energy is increased by that. Well, there's only one unknown here. This is 100 plus 0. This is minus f times 1.6. This is 0, and this is 62.7. And so we solve that using algebra for this f. We get f is 23 newtons. So that is the first part of the problem. Now, in part B, where we're trying to find the velocity that it gets back down here, we use points 1 and 3 as our initial and final points, respectively. So what we know then is that the work other is going to be the work due to friction, but that is going to be friction going up and going down. So it is minus 2 times the 1.6, and we have already found that this is 23, and in fact that is 23.3. I rounded it off up here, but that's 23.3. So if I do that calculation, we get this is minus 74.6. You see, some of it was going up and some of it was going down. The other energy quantities are the kinetic energy is going to be 100 joules as it was before. The potential energy is unchanged between 1 and 3. Those two are equal to each other. And the kinetic energy at point 3 is 1/2 8, and then this is v squared, v sub 3 squared. So that's the unknown speed. So substituting this into our overall equation, then we have the 100 joules minus the total force of friction is going to equal the energy we have at the end, which is the 1/2 8 v squared. And so when we solve that, we get 2.5 meters per second. Now here's a problem dealing with slipping and sliding. A skier falls and loses her ski on a ski slope. The ski then slides down the slope at a constant speed. Which of the following energies are not changing as the ski slides down? And it's a multiple choice. You know what to do. Let's see how you did. Since the ski is moving at a constant speed, its kinetic energy is not changing. However, both the mechanical and potential energy of the ski are changing as it slides down. It's at a different height, so that changes its potential energy, and potential energy is part of the kinetic energy. The mechanical energy then decreases due to the negative work done by the friction. So the potential energy decreases because the height of the ski is decreasing. That means that as you think through the possibilities, that the correct answer is C. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.